Welcome to Math TV with Professor V. In this video, we're going to start Probability Concepts, Chapter 4, and we're going to cover sections 4.1 through 4.3, Probability Basics, Events, and some rules of probability. So terms to know. The probability of an event is the likelihood of the event occurring. You could also think of it as the chance of the event occurring. And a probability experiment is a chance process that leads to well-defined results called outcomes, something that could be replicated usually. And the sample space is the set of all possible outcomes of a probability experiment. So we're going to look at some examples right now so this terminology can start to make a little bit more sense to you. So say we're considering flipping a coin to be a probability experiment. And just check that, it works with our definition. It's a chance process, right? You don't know what the outcome's going to be every time you flip a coin. And we have well-defined results called outcomes. It's clear after you flip a coin what the result is. It's not ambiguous. And the sample space, which is what we're going to be finding here, is the set of all of the possible outcomes. So think when you flip a coin, just a fair coin, okay, nothing fancy schmancy. What are the possible outcomes? Well, either the coin lands heads or tails. So I can use the H to represent heads, T for tails. Sometimes you'll just see sample spaces listed this way, or it is a set. So if you want to use set notation and put braces, that's all the more proper. Go you. Okay, next probability experiment we're going to consider is rolling a die. We'll just roll a regular fair die, 6 sides. And so it could land any number 1 through 6. And I'll list each of those in my sample space. So 1, 2, 3, 4, 5, and 6. All right. Last experiment we're going to consider is flipping 2 coins. Okay. So if you're flipping 2 coins, there's actually 4 possible outcomes, because if the first coin lands heads, the second one could also. But if the first coin lands heads, the second one could land tails. And then similarly, the first coin could land tails, so does the second, or first coin lands tails, second coin lands heads. So there's 4 outcomes there. I'm going to list them all here in my sample space. Heads, heads, tails, tails, heads, tails, tails, heads. All right. Good. Now we're going to consider a standard deck of cards. So find the sample space for drawing 1 card. You're just picking 1 card from a standard deck. And I've just put down here a little image. If you're not familiar with a standard deck of cards, there's 4 suits. So here we've got spades, hearts, diamonds, clubs. They go ace, 2, 3, 4, all the way up to 10, and then jack, queen, king. I mean, sometimes aces are considered high. It doesn't really matter. For probability purposes, you just want to know how many and what you're dealing with. And there's 52 cards in a deck total. So notice 1, 2, 3, 4 different suits. 1, 2, 3, 4. There's 13 across here. Half of the cards are red, half of the cards are black. You're going to need to be familiar just with the basics of a standard deck of cards to answer several of the homework exercises that deal with probability. Okay? If you're not familiar, then just go buy a deck of cards and start playing around this weekend. That's part of your assignment. So find the sample space. I mean, I'm not going to sit here and list out each different card, but technically there's 52 different outcomes that comprise the sample space when you're drawing 1 card from a deck. So I'm just going to say that there's 52 different outcomes. I'm not going to list them all though, okay? Good. Next example, what is the size, so just the size of the sample space for rolling 2 dice? And here actually we have a little chart to help organize all of the possible outcomes. So here's die 1. You can roll 1 through 6. And then here's die 2. Again, you could roll 1 through 6. And here's all the possible outcomes or combinations that could result from rolling 2 dice. So notice you could get 1 and 1, 2 and 1, 3 and 1, etc., all the way through 6 and 6. So take a second, how many different outcomes are here or comprise the sample space? There's 36, aren't there? Good. And this is a basic probability rule for counting that you'll learn when you're trying to figure out how many combinations to make. If there's 6 outcomes for one event and then 6 outcomes for the other event, then you just multiply them by each other to get the total number of combinations or outcomes. All right, very good. Let's look at something a little different. Find the sample space for the gender of children if a family has 3 children. And we're going to use a tree diagram to organize everything. So we want to see what are all the different outcomes that are possible for a family if they're going to have 3 children. Are they going to have boy, girl, 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 boy, girl? You know, it can kind of get overwhelming if you try to just sit there and list them all. You can do it. I have a pretty good systematic way of doing it, but a tree diagram often helps. So this is how you set it up. For the first branch, this is like baby number 1, okay? Either they're going to have a boy or a girl, and then you're going to make another branch off each of these for baby number 2. So baby number 2 could either be a boy or a girl. Same thing down here. And then baby number 3 is going to have a branch off of each of these now. So here's a boy or a girl, a boy or a girl, baby number 3, a boy or a girl, boy or girl. Okay, so you don't have to put the numbers. I'm just showing you what each of the branches on the tree represents, okay? Now here's how you put the sample space together with this. You start at baby number 1, and then you follow each of the branches all the way to the end, okay, until you've gone up every branch of your tree. So this one would be boy, 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 okay, boy, boy, boy. Then this next one would be boy, boy, girl, boy, boy, girl. Then you would have boy, girl, boy. Let's go to the next one, boy, girl, girl. And then I've done all of the ones where they have a boy first. So then now we go, oops, I didn't want to erase. Girl, boy, boy. And then girl, boy, girl. Okay. Girl, girl, boy. Ooh. And I think there's one more. Yeah. Girl, girl, girl. So this is the sample space, okay? If you want, you could put it in set notation. How many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes. Okay, very good. We'll refer back to this example later, okay? So just kind of keep it in mind. Some more terms. An event, when we talk about probability, an event consists of a set of outcomes for a probability experiment. And a simple event is an event with only one outcome, while a compound event is an event with 2 or more outcomes. So I actually wanted to give you some examples. I stuck them down here. So if you flip a coin, okay, it could either land heads or tails. So that's a simple event. But if you flip 2 coins, we saw the sample space earlier. It could be heads, 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 tails, tails, heads, or tails, tails. These are compound events. because they have 2 or more outcomes. Okay? Good. And for events, we can often use Venn diagrams to represent probabilities and outcomes, which we're going to get more into probabilities in a minute. But right now, if we're just talking about outcomes, say you have an event like flip a coin and it lands heads. So if you call landing heads E, then not E would be landing tails, which would be everything outside of the event E. Sometimes certain events can occur at the same time, in which case there's an overlap. And this intersection or overlap is what we refer to as 2 events, A and B, happening simultaneously. This is A and B. And that's how you would illustrate it. And then if you have 2 events and you're interested in when either of them happens or the union A or B, then both events in their entirety get shaded together. Okay? The overlap and each of them separately. So there's different interpretations for probability. We're going to go through 3 of them. First one is classical probability. So classical probability uses sample spaces, which we just found, to determine the numerical probability that an event will happen. And in classical probability, it is assumed that all outcomes are equally likely to occur. That's the big point here. So for example, when we flip a coin and you're computing the probability of it landing heads, when you use classical probability, you're assuming you have an equal chance of the coin landing heads or tails. Is that true? There's some discussion, right? That the shape of the coin and the way it is on one of the sides tends to make it land a certain way. It's actually not 50-50, but we don't get into that when we do classical probability. So the formula when you're computing the probability of any event, the probability of event E is the number of outcomes in E, or think of it like the number of different ways that E can happen, divided by the total number of outcomes or the size of the sample space. And the textbook that we're using right now, it uses this same formula. They just kind of call it something different. They say P, or probability, equals F over N. Okay, same thing. So F is the frequency of the event E. So how many different ways it can happen. And then N, capital N down here, is the total number of outcomes, which is the size of your sample space, okay? So just so you know, when you're doing your homework, if you see this F divided by N business, that's what they're talking about. And then probabilities, we can express them as fractions, as decimals, as percents. Just kind of look at the problem. If it already is working with decimals, then stay with decimals. If they've got fractions, stay with fractions. Usually let the example set the tone. And then if they don't say, then you can just do whatever you want. And general rounding rule, you want to give decimal answers to about 2 or 3 decimal places. Usually the problem will specify how many, okay? And then your fractions definitely need to be in lowest terms, meaning reduce them, okay? Reduced fractions only. Don't give me no 2/10, okay? That's 1/5. Yes? All right, good. So let's look at some examples now. You remember that sample space that we had earlier where we made the tree diagram for that family that they were having 3 kids? Very brave of them. Okay, so we're going to talk about them again right now. For a family with 3 children, find the probability that 2 are girls and 1 is a boy. Okay, so let's actually go back and look at that sample space. We want the ones where there's 2 girls and 1 boy. 2 girls and 1 boy. So that's here, here, and here, right? Those are all of the outcomes that resulted in 2 girls and 1 boy. That's 3 different outcomes, and there were 8 total. So now let me go back here. So this happened 3 different ways. If you want, I'll remind you, it was girl, girl, boy, girl, and boy, girl, girl. And there were 8 outcomes total. So the probability is 3 divided by 8, okay? And then, like your book might say, the probability if you want to think of it as F divided by N, frequency was 3, N is 8, whatever, okay? Good. Let's look back at our deck of cards example. So just a standard deck, 52 cards. A card is drawn from a deck. Find the probability of getting an ace. So how many aces are in a deck of cards? There's 4, yes, 4 out of 52. And this is not reduced. Your answer has to be in lowest terms. So I can divide numerator and denominator by 4. This is 1 over 13. All right, very good. Same deck of cards, find the probability of getting the 2 of diamonds. So the 2 of diamonds, there's only one of those in an entire deck of cards. So that probability is just going to be 1 over 52. That's already reduced, so we're done. Good? Okay, let's look at a different example. In the game of craps using 2 dice, okay, a person wins on the first roll if a 7 or an 11 is rolled. Find the probability of winning on the first roll, and then is it likely to win on the first roll? We'll talk about that. Okay, so game of craps uses 2 dice, and we looked earlier at the size of the sample space. When you roll 2 dice, do you remember how many outcomes there were? There's 36 total outcomes, okay? And the way to win is if you get a 7 or an 11. All right, well, how could you roll a 7? Let's think about it. You've got 2 dice, right? 2 die. So you could get a 3 and a 4. That would give you a 7. Or a 4 and a 3. What else? You could roll a 2 and a 5, or a 5 and a 2. Is there anything else? Yeah, 6 and 1, or 1 and 6. Okay, so there's 6 ways that you could roll a 7. You could also win if you roll an 11. So how many ways can you roll an 11? Just 2, right? A 5 and a 6, or 6 and 5. Okay, so there's 8 different ways to win, and there's 36 total outcomes. So that means the probability of winning is going to be 8 divided by 36. Now we have to reduce this. So I can divide numerator and denominator by 4, right? Divide by 4, divide by 4. So then we're going to have 2 over 9. Okay, so that's answering that first question. Find the probability of winning on the first roll. Now they're asking us something else. They're saying, is it likely to win on the first roll? Anytime you're asked that question, likely, that means more than a 50% chance, right? Or more than half. So is 2 over 9, 2/9, is that bigger than 1/2? No, it's not, right? If you can't compare your fractions, then you can just get a common denominator, okay? Or just think, what's half of 9? 4.5, right? So 4.5 over 9 would be 1/2. So 2 is way less than that. So since 2/9 is less than 1/2, then we say no, it's not likely to win on the first roll. Okay, that's the reasoning. So anytime you're asked if something's likely, compare it to 50% or 1/2. If it's more, yes, it's likely. If it's not, then no. If it's exactly right on the dot, 50%, then it's equally likely, right? Not more. Okay, let's move on. 4 basic probability rules. So rule number 1, the probability of an event E is a number between and including 0 and 1. So we write that the probability of event E is greater than or equal to 0 and less than or equal to 1. So what this means for us is that a probability is never negative and it's never greater than 1. Okay? So if someone tells you there is a 200% chance that I will come see you tomorrow, They're lying, you guys. You can't have probabilities greater than 1, which equates to 100%. All right. Example, if you roll a die, what is the probability of getting an odd number? So how many odd numbers could you roll? 1, 3, or 5. And we know that there's 6 outcomes, right, when you roll a die. So 3 are odd out of 6 total. So this is 1/2. And this is just to illustrate that this probability here, 1/2, is a number between 0 and 1. It's 0.5 as a decimal, if you like that better. And it's not negative, not greater than 1. Rule number 2 of probability. If an event cannot occur, if it's impossible, then the probability is 0. So say I asked you the following question. If you roll a die, what's the probability of getting a number greater than 6? Well, are there any numbers greater than 6 on a regular die? We're not getting fancy schmancy. No, right? So the probability of that happening is 0. Impossible. Not going to happen. Rule number 3. If an event is certain, then its probability is 1. If you know for sure it's going to happen. Let's look at an example. If you roll a die, what is the probability of getting a number less than 10? Well, when you roll a standard die, all of the numbers are less than 10. So all 6 outcomes out of 6 total will be less than 10, which gives me a probability of 1. And then the last probability rule is that the sum, so if you add up all of the probabilities of all the outcomes in a sample space, again, you get 1. Basically, all of the probabilities add up to 100%. Okay, those are just 4 basic facts. We're going to use them to compute probabilities later on. Complementary events. So terms to know. The complement of an event E, and notice how we spell it, complement. This is an E after the L, okay? Not an I. Like when you compliment someone and you tell them your hair looks lovely today, that's a different kind of compliment. Okay, the complement of an event E is the set of outcomes in a sample space that are not included in the outcomes of event E. And the complement of E is denoted E with a little bar on the top of it. Do you see that? So that means the complement of E. So let's look at some examples just so we get an idea what an event is and what its complement would represent, okay? So find the complement of each event. First one is rolling a die and getting an even number. What would be the complement of that event? It's almost like the opposite, but I don't want to use that word because that's not precise enough, but just think not this thing happening. So what's equivalent to not getting an even number? Getting an odd number. So the complement would be rolling a die and getting an odd number. Okay, so far so good? All right, let's look at a couple more. Actually, just one more. Selecting a card from a standard deck and getting a heart. So if that's the event, what's not that happening? Selecting a card from a standard deck and not getting a heart. Instead of saying not getting a heart, you could also say getting an ace, club, or diamond. Okay, same thing. Now, an event and its complement have certain properties when it comes to the rules of probability. So if you look at the probability of an event and you add the probability of its complement, this will always equal 1. Or equivalently, the probability of an event is equal to 1 minus the probability of its complement. And these are interchangeable, okay? So let's look at some examples. And you probably know this. You probably do this on an everyday basis without realizing that you're using a rule that has to deal with complementary events and their probabilities. It's kind of common sense for a lot of examples. So first one, in 2004, 57.2% of all enrolled college students were female. Choose one enrolled student at random. What is the probability that the student was male? Okay, so 57.2% is probability of event E of a female being enrolled in college. I'm going to change that to a decimal, so 0.572. That's the probability of E. And they want the probability that a randomly selected student is male, so that's the complement. So probability of E complement would be 1 minus 0.572, which gives me 0.428. And since the problem gave me the probability as a percentage originally, then I'm just going to write my final answer as 42.8%. Okay. Another way that you could do this, if you want to just keep everything in percentages, instead of doing 1 minus, then do 100 minus, right? So just multiply everything by 100. So, or we could have just done 100% minus 57.2%, and then that gives us the 42.8%. Okay? Good. So this is all having to do with classical probability. Now we're going to go into empirical probability. And empirical probability does not assume that all outcomes are equally likely. Instead, empirical probability relies on observation to determine the likelihood of outcomes. So this is really a more appropriate time to use frequency divided by n, because frequency usually deals with how many times you observe something when you're collecting data, which is why this is like an empirical approach for probability. And so you have a frequency distribution, and the probability of an event E being in a given class or belonging to a certain group is as follows: the frequency for the class divided by the total frequencies in the distribution. So same method to compute. It's just you're going to rely on observations or data that's collected instead of just sitting there and theorizing about what's possible. You'll see what I mean in just a second, okay? So first example, 20 people were tested for their blood types. The results were as follows. So see, we have some sort of data that's being given to us when we're doing empirical probability to help us compute these probabilities. So here's the blood type A, B or O, and the following frequencies. Find the probability that a person has type O blood. Okay, so type O, in this sample of 20 people, there were 7 people who had type O. So the probability would be just 7 out of 20. I'm using this data set. This is empirical. If we were doing classical probability, remember classical assumes everything is equally likely. So you would just say, oh, there's 4 different blood types. If I'm picking someone at random, it should be 1/4. That's not appropriate here though, because we know that it's not equally likely for someone to have any one of the 4 blood types. There's a lot more going on, and some are more common than others. So collecting data and using empirical probability is more appropriate for this case. Now, do I love that there were only 20 people in the sample? No, but we're doing what we can. Okay, part B, find the probability that a person has type A or type AB blood. Okay, so 8 people had type A, 2 people had type AB. So there's 8 of these, 2 of these. So altogether, that's 10 outcomes, right, out of the 20, which is 1/2. All right, good. So this is just empirical because you're using collected data from a sample. And as a note, the law of large numbers is a theorem that connects the empirical probability of an event to its theoretical probability. So basically, the larger your sample is, or the more often you conduct a probability experiment as n gets large, then the empirical probability, what you observe, what you collect, of an event gets closer and closer to the theoretical probability. Like if you think about it, okay, I'm going to put it in like a really clear example. It is possible to flip a coin, say 10 times, and every single time it lands tails. Does that mean that, oh, you have 100% chance when you flip a coin of it landing tails and 0% chance of it landing heads? No, that was just a fluke, right? But the law of large numbers tells us, well, you only flip the coin 10 times. If you flip it 100 times or 1,000 times, the bigger and bigger the experiment, or the more often it's repeated, then the likelihood of you getting some fluke lessens. And so the empirical probability, what you observe from all your coin flips, will approach the theoretical. So it should level out and get closer to half and half if you repeat something often enough, which is why we like big sample sizes, right? When we're collecting data. Okay, enough about that. Subjective probability uses a probability value based on an educated guess or estimate, and it uses opinions and exact information. So there's like no actual calculation going on. It's just you sitting around making up stuff. I'm serious. So say you apply for a job and it's you versus one other person, okay? You and one candidate. And in your mind, this is why it's subjective. In your mind, you're like, hey, they're just as qualified as I am. I think it's a 50% chance that either of us is going to get the job. So that's totally subjective. That's just you sitting around thinking you're just as qualified as them. What's another one? You studied all weekend for your statistics test and you feel super ready. So you're like, I got a 99% chance of passing. Just silly stuff like that. You'll hear people say things like this all the time. Now that I've alerted you to it, you're going to notice it more. Perhaps it will bother you. Okay, enough about that. Let's move on to the addition rules for probability. So you're going to hear this term a lot, mutually exclusive. Two events are mutually exclusive if they cannot occur or cannot happen at the same time. So look here, events A and B are illustrated, and notice there's no overlap. So A and B, these are mutually exclusive. They cannot happen at the same time. In the next diagram, notice there's this little sliver of overlap right here for events A and B. So these two events are not mutually exclusive. Why does this matter? Because it affects how we have to compute the probabilities, okay, of these events occurring. So let's just first practice identifying whether or not two events are mutually exclusive, okay? So example 1, rolling a die and getting an even number, that's one event. Let's call it event A. Or roll a die and get a number less than 3. So are these two events mutually exclusive? Can they happen at the same time or not? Easiest way is just list out all of the ways each of the events can happen. List their sample spaces. So for event A, if you roll a die and get an even number, that could happen if you roll a 2 or a 4 or a 6, yes? How can event B happen? You roll a die and you get a number less than 3. So that happens if you roll a 1 or a 2. I can't include 3 in there because they said less than 3, okay? Now look at these two sets here, A and B. Is there any overlap? Is it possible for something to happen that belongs to both A and B at the same time? Yes, look, 2. 2 belongs to both sets. So are the two events mutually exclusive? No, they're not mutually exclusive. 2 is in both. They can happen at the same time. All right, let's look at another example. Can you draw a card from a standard deck and get a heart or get a spade? Well, those are two completely different suits. You'll never have a card that's a heart and a spade at the same time. I'm not going to list out each of the sample spaces. There's 13 hearts, there's 13 spades, but none of them overlap. So if there's no overlap, then we say yes, the events are mutually exclusive, okay? No overlap means yes, mutually exclusive. All right, so here's our first probability rule to compute when you do have two events that are mutually exclusive. The probability that A or B will occur is the probability of A plus the probability of B, okay? And if you want, let's make a little diagram here. So remember, the probability of all of the outcomes in a sample space is always 1. And here I'm going to have like event A, and we just said that it's mutually exclusive with event B, so there's no overlap. So if you want the probability of A or B, then you take the probability of A and you add it to the probability of B. So you're going to take this plus this. Okay, good. Here's an example. At a community swimming pool, there are 2 managers, 8 lifeguards, 3 concession stand clerks, and 2 maintenance people. If a person is selected at random, find the probability that the person is either a lifeguard or a manager. Okay, so altogether, how many people are working at this swimming pool? 2 plus 8 plus 3 plus 2. So there's 15 people total. And they want the probability that the person is either a lifeguard or a manager. And you can't have more than one job at this pool, okay? So there's 8 lifeguards and 2 managers. So we're just going to add their probabilities together. So probability of someone being a lifeguard picked at random would be 8 over 15. Probability that someone's a manager is 2 over 15. And then now we're going to add these together. So 8 plus 2, that's 10 over 15. And reduce your fraction, I can divide by 5, right? So that's 2/3. Good. Let's look at another example. At a used book sale, 100 books are adult books and 160 are children's books. Of the adult books, 70 are nonfiction, while 60 of the children's books are nonfiction. If a book is selected at random, find the probability that it is an adult book or a children's nonfiction book. Okay, so altogether, how many books are there at this book sale? Well, there's 100 adult books and 160 children's books, so 260. And they want the probability that we get an adult book or children's nonfiction. So that's going to be the probability of getting an adult book plus the probability of a children's nonfiction book. So altogether, there are 100 books that are for adults. So that's 100 out of 260. And then how many children's nonfiction are there? Only 60. So 60 out of the 260. And then add these up. So 100 plus 60, that's 160. Don't change the denominator when you add your fractions, okay? And then look, you don't need a calculator. We can reduce this on our own. The zeros cancel. 16 divided by 26, you can cut each of those in half. That's 8 over 13. All right, good. Now, you might be wondering, well, what if the events are mutually exclusive? Are not, excuse me. What if the events are not mutually exclusive? Well, then we have to be careful that we don't count that overlap twice. So when you have events that are not mutually exclusive, meaning they can happen at the same time, then the probability of A or B, it's still probability of A plus probability of B, but then you subtract the probability of A and B. Watch, using the Venn diagram. If you take the probability of A, you're taking all of this, right, that I'm shading here. And then if you add to that the probability of B, then you're adding this piece. But notice I counted the overlap twice, right? Once with A, once with B. So this right here, that overlap, that's the probability of A and B. And that's why we subtract it at the end, because it got counted doubly. I know. Okay, so that's all you have to do when you have two events that are not mutually exclusive. So let's try here. A single card is drawn from a standard deck. Find the probability of selecting the following. So first, probability of getting a 4 or a diamond. So that's going to be the probability of getting a 4, or I'm going to put plus the probability of getting a diamond. And then I'm going to subtract the probability of getting 4 and a diamond. So let's see, what's the probability of drawing a 4 in a deck of cards? How many are there? There's 4, right, out of 52. And then how many diamonds are in a deck of cards? There's 13. Minus, can you get a card that's a 4 and a diamond? You sure can, that 4 diamonds, right? So minus 1 out of 52. Because if you think about it, we counted that 4 of diamonds twice. I counted it here with all the 4s, and then I counted it again with all the diamonds. So we got to take one of them out. 4 plus 13, that's 17, minus 1, that gives us 16 out of 52. And then I can divide top and bottom by 4. So this is 4 over 13. Good. Next example, what's the probability of getting a jack or a black card? Okay, so that's going to be the probability of getting a jack plus the probability of getting a black card minus the probability of getting a blackjack. So jack and black. All right, so how many jacks are in the deck? There's 4, right? So 4 out of 52 plus how many black cards are in the deck? Half of them, right? So 26 out of 52 minus how many jacks are black? There's 2, right? You have your spades and your clubs. So jack of spades, jack of clubs, those are both black, and I've doubly counted them. So minus 2 out of 52. So altogether, we've got 4 plus 26, that's 30, minus 2, 28 out of 52. Can we reduce this guy? Yep, divide by 4, so 7 over 13. All right. Which event is more likely to occur? So which one has the higher probability? This one right here, 7 out of 13 is more than 4 out of 13. So jack or black is more likely. Okay, one more example. A local postal carrier distributes first-class letters, advertisements, and magazines. For a certain date, she distributed the following numbers of each type of item. The information has been organized into the contingency table below. So she delivers mail to homes and businesses, first-class letters, ads, and magazines. First part says, if an item of mail is selected at random, find these probabilities that the item went to a home. So really what I need to do first is get totals so I know how many pieces of mail we're working with altogether. So let's start adding everything up. Total. Sum up each of the rows, each of the columns, okay? So how many first-class letters were there? 1,057. How many ads? 1,427. And magazines, 300. If I add this whole row, that'll tell me how many pieces of mail she delivered altogether. And this is 2,784. Excuse me. And then I'm also going to sum up across each of the rows here. So all of the home deliveries, she delivered 934 pieces of mail, and the businesses 1,850. And also, you guys, the 934 and the 1850 right here, these should sum up to the total as well. So you can double check that you did all your addition correctly that way. Okay, so now we have everything we need. Let's see, the first part says, if an item of mail is selected at random, find the probability that it went to a home. Okay, so again, we're just gonna do probability is, your book loves writing F divided by N. So how many home pieces of mail were delivered? There were 934, right? We don't care if it was first class ad magazine. So 934 divided by the total, 2784. Here's a good example. Like, I'm not going to leave this as a fraction because it's not a simple one where I can look at it and say, oh, that's about half or less than half, or, you know, it's just like a weird, ugly numbers. So give it as a decimal, punch it in your calculator. Let's round to 3 decimal places, 0.335. Then it actually means something to me. I can look at it and say, oh, it's about 1/3 of the mail delivered went to a home, you know? Okay, next one, the item was an ad or it went to a business. Or, so we need the probability that it was an ad plus the probability that it went to a business minus the probability it was an ad and went to a business. Okay, so how many were ads? 1427 out of 2784. How many went to a business? 1850 over 2784 minus, what did we double count? How many ads went to businesses? 1,021. So subtract that. We counted those twice out of 2784. Okay, so then make it a decimal at the very end. Don't get out of control. 1427 plus 1850 minus 1021. That's 2256 over 2784. Now, can you hear me punching it in the calculator? Okay. As a decimal, that's 0.810. Good. Yes, perfect. All right, good job. How do you guys feel? You're gonna have some like this in your homework, but you should be under control. And then I'm just gonna do one fancy little example, but don't stress, okay? This is just for fun. The last idea that we're going to work on in this video is the addition rule for 3 or more events. Now, if the events are mutually exclusive, then it's pretty easy to compute the probability. The probability of A or B or C happening would just be the probability of A plus the probability of B plus the probability of C. But what if the events are not mutually exclusive, meaning some of them can happen at the same time? Well, then the formula gets a little more complicated, and there's a Venn diagram here below to help us organize exactly what's going on. So let's go through it together. The probability of A or B or C, it starts off the same, probability of A plus probability of B plus probability of C. Then you want to subtract the overlaps where you would be double counting some of the probabilities. So then we subtract the probability of A and B. That would be all of this right here. And then we subtract the probability of A and C, which would be this entire region right here. And then lastly, we subtract probability of B and C. So then we subtract this portion now. We have to add back the probability of A and B and C, which is this, you know what? Let me color it in black because I don't think you can see it with the highlighter. We're adding back where all 3 overlap because it got subtracted too many times is the idea. Okay, so that's the formula. You will not be required to do probability for 3 events on the exam or anything like that, but I just wanted to work through one example with you so you could see how it unfurls, okay? So there's the Venn diagram. Let's just go back to a nice card example, since hopefully we're all pretty familiar with that. So a single card is drawn from a deck, standard deck. Find the probability of selecting. Part 1 says, an ace or a 10 or a club. All right, I don't really feel like writing out ace, 10, club, so I'm just going to call each of these events something. I'll say let event A be that you draw an ace. Let event B be that you draw a 10. And let event C be that you draw a club. All right? So what we're trying to do is figure out the probability of A or B or C happening. Let's write the formula out. So this is probability of A plus probability of B plus probability of C minus probability of A and B minus probability of A and C minus probability of B and C, and then we add back probability of A and B. That's my and sign. I'm running out of space. Bear with me. And C. Okay, let's go through step by step. We're just going to think of our standard deck. Probability of A. What's the probability that you draw an ace out of a standard deck? Well, how many aces are there? There's 4, right? So this is 4 out of 52. Plus probability of B. What's the probability that you draw 10? So how many 10s are in a deck? There's 4 also. Plus probability of C. Probability that you draw a club. Well, that's one of the 4 suits. So there's 13. Oh, why did I put 10? That should be a 52. There's 13 out of 52. Minus, okay, let's be careful here. Probability of A and B. So what's the probability that you get an ace and a 10? Well, that's impossible. You can't get a card that's simultaneously an ace and a 10. So the probability is 0 out of 52, or you could just put 0. Minus probability of A and C. So you get an ace and at the same time it's a club. Can that happen? Why, yes, if you get the ace of clubs. So 1 out of 52 for that guy. Minus probability of B and C. So how many 10s are there that are also clubs? Can that happen? Yes, again, the 10 of clubs. Minus 1 out of 52. So here. Probability of A and B, 0. Probability of A and C, 1 out of 52. Probability of B and C, 1 out of 52. Who's left? Probability of A and B and C. So can you get a card that is an ace and a 10 and a club? No way. So plus 0 out of 52. Let me highlight that in yellow. And then this is also why I recommend, like, don't reduce the fractions until the very end, because see, like 13 out of 52 is 1/4, but see how lovely it is right now? Everything has a common denominator. Aren't we appreciating? Okay, so 4 plus 4, 8 plus 13, that's 21, minus 1, minus 1. So 21 minus 2, that's 19 out of 52. Does that reduce? No, 19 is prime, so we're just going to box it and be done. And then example 2 says, what's the probability of a jack or king or club or heart? Oh my goodness, that's 4 events. I only gave you a formula for 3. So that's a challenge problem. You can try it on your own if you're feeling adventurous. You can comment down below if you think you have the answer. Maybe I'll post it on Instagram. And you can Google the formula or see if, you know what would be super fun, draw out a Venn diagram for 4 events and see if you could, you know, come up with what the formula would be. That would be ever so clever. But anyways, this was all optional. Just for the exam, you're going to be responsible for addition rule with just 2 events like we did earlier in the video. Okay, don't stress. So please give this video a thumbs up if you enjoyed it. Subscribe to my channel if you haven't already, and then feel free to browse around, check out the other playlists. I have video lectures on Calc 1, 2, 3, obviously the rest of introductory statistics, trig, pre-calc, all that good stuff. So see you guys soon. Take care. Bye.